Welcome to Chapter 3 of the NIMO Introduction series. In this chapter, we'll take a deep dive into the AI optimization algorithms that power NIMO. You'll learn how these algorithms intelligently select the next experiment to run, maximizing your chances of finding optimal materials while minimizing the number of experiments needed. By the end, you'll know exactly which algorithm to choose for your specific optimization problem. Before we discuss specific algorithms, we need to understand the fundamental challenge in optimization, the exploration-exploitation trade-off. Exploration means testing regions where we have little information, potentially discovering better solutions in unexplored areas. Exploitation means focusing on regions where we've already found good results, refining our best solutions. The challenge is that we can't do both at the same time. Good optimization algorithms automatically balance these two strategies, knowing when to explore new territory and when to exploit known good regions. PHYSBO is NIMO's flagship algorithm, based on Bayesian optimization principles. It works in three main steps. First, it builds a surrogate model using a Gaussian process to approximate the objective function based on existing experimental data. The Gaussian process gives us not just predictions, but also uncertainty estimates. Second, it computes an acquisition function that identifies where the next experiment is most likely to improve results. Third, it selects the candidate that maximizes this acquisition function. After running the experiment, the new data is added, and the cycle repeats. This approach is incredibly sample efficient. PHYSBO supports three acquisition functions, each with different characteristics. Expected improvement, or EI, provides a balanced approach and is the default choice for most materials science problems. It naturally adapts to the optimization landscape. Probability of improvement, or PI, is more exploitation-heavy, focusing on regions near the current best. Use it when you're close to optimal and need refinement. Thompson sampling, or TS, is more exploration-heavy and works well for multimodal functions or when running parallel experiments. For most situations, I recommend starting with expected improvement. Random exploration, or RE, is simple but essential. It randomly selects from untested candidates. You might wonder why we need this when we have intelligent algorithms like PHYSBO. The answer is that PHYSBO needs initial data to build its model. In the first cycle, when you have no experimental data yet, RE provides an unbiased starting point. It's also useful as a baseline comparison to validate that AI is actually helping, and in situations of high uncertainty when you have no prior knowledge about the search space. The typical workflow is to use RE for cycle 1, then switch to PHYSBO for all subsequent cycles. BLOX uses random forest models instead of Gaussian processes. While PHYSBO with Gaussian processes provides well-calibrated uncertainty estimates, it can become slow when dealing with many descriptors. BLOX offers a faster alternative for high-dimensional problems. The rule of thumb is, use PHYSBO when you have 20 or fewer descriptors, and consider BLOX when you have more than 20 descriptors. Both algorithms are effective, but BLOX scales better as the number of features increases. The uncertainty estimates from BLOX are approximate rather than exact, but for practical optimization, this is usually sufficient. Real materials optimization often involves multiple objectives that may conflict. For example, you might want to maximize strength while minimizing cost. This is where multi-objective algorithms come in. PTR, or Pareto-based Thompson ranking, handles these scenarios by finding Pareto optimal solutions. A solution is Pareto optimal if no objective can be improved without worsening another. Instead of a single best solution, you get a Pareto front, a set of optimal trade-offs. Simply set the number of objectives parameter to 2 or more, and NIMO will find the best compromise solutions for you. With multiple algorithms available, how do you choose? Follow this decision tree. First question, is this your first cycle? If yes, use random exploration to collect initial data. If no, is this multi-objective? If you're optimizing more than one property, use PTR for 2 objectives or BOMP for more. If it's single objective, ask, do you have more than 20 descriptors? If yes, use BLOX for speed. If no, are you mapping phase diagrams? If yes, use PDC, which is designed specifically for phase boundary identification. Otherwise, use PHYSBO as your default choice. This decision tree will guide you to the right algorithm for any scenario. Here's a quick reference table to summarize algorithm selection. For first experiments, use RE to collect initial random data. For general optimization tasks, PHYSBO gives the best overall performance. For high-dimensional problems with more than 20 features, BLOX is faster. For phase mapping in alloy systems, PDC is specifically designed for that task. For multi-objective optimization, PTR handles Pareto optimization. And for fast exploration when you need quick candidate selection, consider SLESA. Keep this table handy when starting new optimization projects. Let's summarize what we've learned. PHYSBO using Bayesian optimization is the default choice for most problems because it balances exploration and exploitation automatically. Random exploration is essential for collecting initial data in your first cycle. BLOX scales better for high-dimensional problems with more than 20 features. PDC is specialized for phase diagram construction. And PTR handles multi-objective optimization when you need to optimize multiple properties simultaneously. Remember the key workflow. Always start with RE for cycle 1, then switch to intelligent algorithms. In Chapter 4, we'll put this knowledge into practice with a hands-on tutorial. See you there.